Hello, everybody. My name is Enrico Cancelli, and I'm one of the authors of Exploiting Proximity-Aware Tasks for Embodied Social Navigation. Our work deals with embodied visual navigation in constrained indoor environments. Many types of policies have been proposed in the literature, together with different types of tasks, from the simpler one, like point-call navigation, just call navigation, to more complex one that actually deals with natural language processing. However, most of these tasks do not deal in any way with dynamical scenes, and they do not account for human presence. However, a new challenge, together with a new task called social navigation, has been proposed. In this task, we do not only have to reach a point in space, like point-call navigation, but we also have to avoid collision with humans, like you see in the image on the right. In our work, we experimented with two different large-scale datasets, the first one being Gibson 4+, the second being HM3DS, for which we also provided a new dataset of episodes. Our model extracts information about proximity directly from the simulator. So we have a notion of relative position between agent and each person seen. We extract this complete information and we process it into simpler form to a proximity feature extraction procedure. Those proximity features are then used together with auxiliary tasks to inject some knowledge about proximity directly in our policy architecture model. We devised two different types of proximity features connected with their own auxiliary task. The first is called risk value. The second is proximity compass. Risk value deals with the short range form of proximity and is essentially the inverse of the distance with the closest person. And is represented as a scalar between 0 and 1, where 0 is absence of risk and 1 is collision. Proximity compass is in a way similar, but it deals with a much longer range. And the space is divided into 8 sectors. For each one of these 8 sectors, risk values are calculated, and then this compass is unrolled into a vector representation. We experimented with different types of configuration. We also mixed our task with self-supervised auxiliary tasks that are general purpose and have been used for also other models. And we made a complete ablation studies, and we found out that the best performing models are the ones that use our task, optionally with the use of self-supervised tasks. Furthermore, we also proposed an encounter-based evaluation procedure that evaluates the behavior of our agent in 4 different types of situation that we deemed interesting. For each one of these classes, we devised 4 metrics, namely number of encounters, encounter survival rate, average linear velocity, average agent-person distance. And we perform a complete evaluation for each one of these classes. From our final results, we can find out that even though some of our models are similar perform in cross-grain metrics, they behave completely different with respect to encounters. So we have different ways of dealing with the same problem. Here we have some qualitative results. For example, this is a success episode where the agent can safely reach the final point while avoiding people. Here we have a suboptimal but successful episode. So we have some backtracking and a very successful avoidance. And at the end, the agent arrives to the goal. And finally, we have an example of a failure where the agent just gets hit by a person that exits from another room. Thank you for your attention.